Good morning, good afternoon. My name is Yaron. Together with my colleagues, Matt and Dario, we're from the JavaScript team. We're working on the rendering engine. The purpose of this demo theater is to walk you through the steps and technique to implement a custom layer for 2D using WebGL. We're assuming some sort of knowledge about WebGL, so we won't go into all the details. What we're talking about is highly geeky. I apologize. I don't know if we're going to have time to get questions, so we can get questions at the very end at the JavaScript island after the demo theater is done. I'll start with giving a very short introduction. Dario is going to do the walkthrough itself. And eventually Matt will conclude with some part about gotcha, something to consider when implementing WebGL, and then some points about what we're considering adding in the future. So a little bit, very quick rough overview about the 2D rendering engine. It was originally implemented using SVG. We figured out that it does not meet the requirements of the performance and doesn't scale as well, so we ported it over to WebGL. Since version 4.10, all the rendering is done with WebGL, so the entire rendering stack is based on WebGL. For those of you who don't know, WebGL is a JavaScript-based API, which under the hood calls a native API such as OpenGL, DirectX, Vulkan, or Metal. And that in turn communicates with the graphics card, either dedicated or on-chip. The rendering engine of the JavaScript API is built, take advantage of WebGL, basically entirely implemented with it. We've designed and built it as a geographical rendering engine. It's internally quite generic and scalable, and we constantly evolve it, making it more scalable, faster, and adding more and more capabilities. From 30,000 feet above, if I look at the components of the rendering engine, we can divide it into two main parts. There's the part that maintain and handle the mesh. If you consider a mesh is basically what breaks the geographical entities, such as geometries and symbols, into triangles and textures, buffers, and shaders, and so on. So the mesh is responsible for doing that. This is usually very CPU intensive, so we take advantage of web workers to offload the work from the main CPU. We also take advantage of techniques such as quantization and tiling schemes that provide a solution for precision that Matt will touch upon later on in his part. Also provide us mean for level of details and also support for rendering across international date line. The other main part of the engine is the responsible for the actual drawing, and there it's divided into two main categories. There is the memory manager, which basically manages the GPU memory. And it is the one that takes the meshes and add them to the GPU. It handles updates to meshes. It is responsible to optimize draw calls to minimize the number of instructions that we're making against the JavaScript instructions that we generate per frame. And also consider concepts of GIS, such as maintaining the Z order of the features and so on. We also rely on a material system, which is really the system that manage the lifetime of the shaders that are used throughout the rendering or the session of the map. Internally, we use what we're calling a painter API, which basically organizes the drawing of the different components into a set of painters, each responsible for different geometry type. So question, why custom layers? So the JavaScript API is very rich in capabilities, but sometimes there are cases that the developer cannot meet their requirements, and therefore we need to resort to implement a custom layer. This could be for many reasons. One is that there need to be a very tight control over the implementation. There could be specific performance requirements like sub-second or sometimes even less update frequency. It could be integration with third-party rendering engines. And it could be some other or data format that is simply not supported by the out-of-the-box API. And then the question, why layer, not other means of integrating custom rendering? A layer is a well-established concept in the GIS world. When implemented as a layer, that layer becomes just yet another layer that the API can recognize. The user can reorder layers, turn layers on and off, support for heat tests and pop-ups, which are critical with very minimum effort or no effort at all almost. And then so basically that layer behaves just like any other layer. I'll hand it over to Dario to actually show you the walkthrough and show you the technique itself.
Thank you, Yaron. Version 4.11 of the ArcGIS JavaScript API enables the developer to create. It's on, but let's try a little higher. Hello, hello, hello. Version 4.11 of the ArcGIS JavaScript API enables the developer to create custom layer-based WebGL visualizations. Let's try with another one. Cool. Before getting into the details of how this works, I would like to give you a glimpse of what can be accomplished thanks to this new addition to the API. This is an app designed around the idea of interactive postcards to promote a campsite area by a lake. It is a base map enhanced with a layer that uses WebGL to display scenic elements such as these trees swaying in the wind and this realistic water effect. There are also some fire pits with flames and smoke. All these visual elements are influenced by a simulated wind speed and direction. We also implemented a lighting model that enables the user to visualize this scene at different times of the day, such as noon, evening, or night. This is still a map where you can pan, zoom, rotate, and take advantage of all the features of the JavaScript API, such as pop-ups, geolocation, widgets, as we are doing here, and screenshot. Using the take screenshot feature, we implemented a photo mode that enables the user to take a picture of what's on screen so that maybe it can be shared or set as a desktop background. Visualization like these that take advantage and integrate with the map view are made possible by an extension API based around the concept of custom layer views and custom layers. To create a custom layer view, the developer starts by subclassing base layer view 2D or base layer view GL 2D, and then must subclass layer or some other suitable layer class, such as graphics layer, to create a new instance of the custom layer view. In this talk, we'll be focusing on WebGL and subclassing base layer view GL 2D. Most of the topics we'll be talking about are covered in detail by an SDK sample. It is a point graphics layer and uses a custom WebGL layer view to display the graphics as radiating rings. It is an app inspired by telecommunications iconography and the concept of broadcasting and transmission. A visualization like this can really help your radio station theme map stand out and be very compelling for the user. This is coming in the SDK for version 4.11 of the API. We encourage you to visit developers.arcgis.com and experiment with the code in the sandbox. You can play with the shaders, for instance. You can make the markers larger. You can change their color. You can increase the number of rings and their speed. In addition to its educational value, this app has some parts that have the potential of being really useful for you in your custom visualizations. For instance, this code that computes the transform matrices used in the shader. We'll be talking about this sample in detail, but first we want to give you an overview of how the Extensibility API works. The developer experience starts by subclassing layer or some other suitable layer class, such as graphic layer. The only mandatory override is create layer view that must return an instance of the custom layer view. You are free to add more methods and properties as needed. In the ArcGIS JavaScript API, the layer is seen as a container of pure data. You may want to keep this in mind while splitting the responsibilities between the layer and the layer view. Layers are normally not concerned with visualization. Layer views are responsible for rendering the data that is contained into a layer. To create a custom layer view, you subclass base layer view GL2D, and you have three methods to override: attach, detach, and render. Again, you can add more properties and methods as needed, but from the point of view of WebGL extensibility, these are the only ones that the API cares about. The attach and detach method act as a constructor-destructor pair. They have access to the WebGL context. The body of the attach method, of the attach override, is normally where you would create the WebGL resources like textures, buffers, and programs that the apps need a startup. All other initialization tasks can be carried out in the constructor. Generally speaking, the detach method is responsible for undoing everything that was done in attach, and possibly more, which usually means destroying all the WebGL resources used by the app. The render method is called at every frame, and its main responsibility is issuing the WebGL commands for the context. Optionally, it can also carry out some resource creation and update tasks as needed. It receives a render parameters object that contains the WebGL rendering context and a view state. The view state is a description of the 2D camera that is looking down the map. Also, the render method has access to the layer and to its data through the this.layer property, which is inherited from the base layer view. At every frame, the render method must draw a visualization of the layer data based on the current view state by sending the appropriate WebGL commands to the context. Something really important to be aware of here is that the WebGL context is shared among all the layers and even with the map view itself that uses it for some internal render tasks. When attach, detach, and render are called, the API ensures that the WebGL is going to be in its default state almost, except for the currently bound frame buffer object, which may not be the default one. You do not have to reset the WebGL state when you're done, because we do it automatically for you. But this also means that every time that render is called, you will have to reconfigure the WebGL state fully and from scratch. Also note that attach, detach, and render are the only methods which are allowed to invoke WebGL. Doing so from elsewhere may actually cause performance issues, and you may even break the rendering of the map view itself. Now we can go back to SDK sample and show how we implemented it. We will show how to subclass base layer view GL2D. We will show how to subclass graphics layer and why we subclass graphics layer instead of the more basic layer. We'll show how to listen for changes in the layer data and have the layer view react to them. We will define the vertex formats, shader program, and transformation matrices used by the app. Finally, we'll wrap this up by showing how to override attach, detach, and render. As a bonus topic, we will show how to implement heat testing for your layer. So the first step is subclassing graphics layer. We decided to subclass a graphics layer instead of the more basic layer class because we want to take advantage of its graphics property, which is perfect for us to store our layer data in the form of point graphics. The only thing that our subclass needs to do is override create layer view to return an instance of the custom layer view. Then we have to create our custom layer view class by subclassing base layer view GL2D because we want to take advantage of WebGL. Before getting into the details of how to override, attach, detach, and render, we will talk about the rendering techniques adopted in this sample. For this, in this sample app, we render the markers using quads. Every quad is made of 2 triangles, 4 vertices, and 6 indices. we use a single vertex buffer and a single index buffer to store all the markers. The position of a vertex is actually split into two attributes. We have a position, which is the geographical position in meters of the center of the marker, and is the same for all vertices of the same quad. And then we have a offset, which is a vector that is different for each vertex and points in the direction from the center of the marker to that vertex. This split between position and offset is useful to implement the anti-rotation, anti-zoom behavior that is typical of markers. So they will not rotate as the map rotates, and their size on screen will always be 70 pixels by 70 pixels. These geometric data, these vertex data, must be updated every time that the layer data changes. To do this in the constructor of the custom layer view, we start listening to the layer.graphics property, and every time that a graphics is added or removed, we set a flag, needs update to true, and we request a new frame, a new render. This eventually will cause the render method to be called, and inside the body of the render method, we will check the state of the needs update flag, and if we find it to be true, we will update the vertex data contained to the vertex buffer and upload the updated data to the GPU with GL buffer data. We do this in two steps using a flag that is set and then read by render, because it would not be safe to invoke WebGL directly from the change data event listener. More on this, we'll expand on this in the final part of the talk. This geometric information is consumed by a vertex shader, which is responsible for positioning and shaping the markers on screen, the quads on screen. It does so by relying on a few transformation matrices. It starts with the position of the marker in meters. The first step is applying the matrix U-transform that is responsible for positioning the 2D camera and converting from meters to pixels. Then we offset the vertices, we offset the vertex in the direction of A offset scaled by size, which is 70. And since A offset has coordinates like 0.5 and minus 0.5, this has the effect of displacing the vertices 35 pixels from the center, left, right, top, and bottom. And we end up with a 70 by 70 pixel markers as we wanted. Finally, we did all our computations in pixels, but we need to update clip space coordinates, and for this there is a final transform matrix which is called UDisplay. The offset vector that was used to shape the marker will also be used in the fragment shading phase, and so we store it into a varying variable. Now let's talk about the matrices that we need to implement these transforms. We will be using GL matrix to do the matrix algebra. So read this code snippet from bottom to top, because that's how GL matrix works. The first step to compute the transform matrix is the 2D camera translation, which is responsible for positioning the 2D camera on the center of the view. Then there is a scaling that depends on the current resolution that we are looking at the map and the device pixel ratio. Then we have to take into account the map rotation. Finally, there is an half screen width translation to the right, half screen height translation down, to take into account the fact that the origin of the screen is in the upper left corner of the screen and not in the center. There is something that we haven't described yet in this slide, and it's this vector. It's a 2D vector, it's called translation to center. Let's talk about it. In a naive implementation, we could define it as the negation of the position of the 2D camera. This is the oldest trick in computer graphics, in which moving the camera there is implemented by moving the scene here. This is totally sound from a mathematical standpoint, but in our GIS settings would lead to problems. The reason is that when we use meters or map units in general, they are relative to the origin of the reference system, which usually is very far away from the camera and from the region of interest. This leads to very large magnitude for the attributes and the uniforms that we are passing to the vertex shader. And since the GPU uses 32-bit floating point arithmetic, we end up with experiencing precision issue that causes the markers to wobble at large scale. So when we zoom in, we see that the position of the marker is unstable. In the SDK sample, we decided to take care to solve this issue by using a local origin. So we define a point called local origin, which is much closer to the 2D camera than the origin of the reference system. All the attributes and the uniforms that we're going to pass to the vertex shader are relative to this point. They are made relative on the CPU in JavaScript by performing the appropriate subtractions. And since JavaScript on the CPU can use 64-bit arithmetic, we don't experience any precision issue. The result of these are much shorter, much smaller magnitude values, and when we pass them to the vertex shader is able to deal with them using 32-bit precision. This is fine for a sample, but this approach does have some drawbacks. The main one is that as the user pans and zooms around, we have to move the local origin, which implies recomputing the position attribute, which then must be re-uploaded to the GPU. And we do this only because we want to keep its magnitude small, not really because the underlying layer data has changed. So it is not ideal, it is not very efficient. We think that the real answer to the problem of precision and to other problems in GIS rendering is another one, and in the final part of the talk we will be discussing that. We did our computation in pixels, but the vertex shader needs to output in clip space, and to do this there is one final matrix transform, which is UDisplay, and this is just a scale and a translation equivalent to an orthographic camera, and it's just scale and translation. So we made it to the fragment shading part. The fragment shader is responsible for computing an alpha value dependent on the position of the fragment in the marker, in the quad. And once it's done with that, since we're using premultiplied alpha, we combine it with the RGB color of the marker and we return. Shading is based on the length of the offset vector, which is 0 at the center of the marker and 0.5 on the outer edge. The final alpha is dependent on two factors, f1 and f2. f1 is a cosine-based factor that is fully opaque at the center of the marker and fully transparent of the edge. f2 is the rings factor, and it uses an increased spatial frequency to allow the cosine to complete several cycles before reaching the edge of the marker. Every cycle leads to a ring. The formula for f2 also depends on the current time, and this is responsible for the radiating animation. The final alpha is the product of f1 and f2. Now we have all the elements to describe how the attach, detach, and render method are overridden. Let's start with attach. Attach uses the WebGL context to compile the shaders, link the program, and once we have the linked program, we can retrieve the uniform locations that we store into properties for later use. This is also a good time to create the vertex and index buffer that we need. They're going to be initially empty. We will fill them up with data later. The render method is responsible for issuing the actual WebGL drawing commands. It starts by binding the program. It then sets the uniforms, binds vertex and index data, configures transparency because remember that we're using premultiplied alpha, and finally with a single indexed call, draw elements, it draws all the markers in the layer. Remember that all the markers live in the same vertex buffer and index buffer. Since this is an animated layer, we want to keep the animation running, and we do that by requesting a new frame by calling this.requestRender, which is inherited from the base layer view. The detach function is responsible for destroying the created WebGL resources and stop listening to the data. This concludes our discussion of the SDK sample as it is now on the developer's website. There is a bonus topic that we want to talk about, which is heat testing. It's not currently covered by SDK sample, but we think it's important to make your layer views more useful. So if you want to make your custom markers heat testable, you override heat test on the layer view. This function receives the XY test position in screen space in pixels. What you will do in the body of the override is something like iterating on the graphics and look for a hit. Usually you would have to take into account the size of your graphic, its shape and its position. In our case, it's very easy because they're all circles and they're all 35 pixels. So if we find a graphic within 35 pixels from the test position, it's a hit. This is enough to make your layer view testable so that when the application calls mapView.hitTest, there is a chance that your graphics will be returned as a result. But you can bring this a step further. There is a default behavior in mapView, which is the default pop-up. When the user clicks on a graphics, a pop-up opens up to display the attributes of that graphic. You can adopt this very useful default behavior simply by setting the source layer property on the graphic that was hit. Doing this with just a few lines of code, you made your layer and layer view fully interactive. All that we talk about is coming in version 4.11 of the API, and we can't wait to see what we will be able to do with custom layers and WebGL. For the final part of the talk, Matt will discuss some of the challenges of implementing custom WebGL visualizations as well as GIS rendering in general. We will also share with you the plans that we have to make the visuals of the API even easier to customize.
All right, thanks, Dario.
Thank you.
So now I'll talk about a few things to consider when implementing your own custom layers, as well as what's next for custom rendering in the JavaScript API. So when thinking about geographical rendering, I think there's two sort of major concerns that can end up being quite problematic. So the first is that, of course, the world is quite a large place. So potentially you have a huge amount of data in a service, but only a small fraction of that data visible at any given point in time. You might also have very detailed geographic data that at the current scale is kind of overkill for what you need. So being able to handle different levels of detail and increase that detail as you zoom in is quite important. Additionally, WebGL only has single precision floats. So like Dario mentioned, you'll need local origins in order to correctly render data. And then of course the world is round. At least that's what the geographers on the team are always telling me. So to support things like wraparound, that will require additional consideration from developers. And tiling provides a pretty straightforward way of solving these two problems. So tiling is pretty ubiquitous in mapping platforms, and it's the approach that we use in the JavaScript API as well. The basic premise behind tiling is that you divide the world into a grid of tiles, with each tile defining a local origin. By making each tile a power of 2, we can cleanly divide each tile into 4 when zooming in one level of detail. And this allows us to display higher resolution data as users zoom in. With a local origin, we can now represent the entire world with single precision floats. And if we do things such as quantizing the data, we can compactly store and transfer data from the server. Additionally, wraparound becomes pretty trivial to support because we can just repeat tiles. Moving on from tiling, you also want to make sure that you're careful of managing WebGL State. So WebGL consists of managing a series of global state objects. And the issue with that is that both custom layer code and the API will be contending over those same shared resources. To handle this, we reset the state when we call custom layer code. But what that means is that you'll need to make sure that you set state variables before calling your own draw code. The only exception to this being the bound frame buffer, which you will want to target. We will bind the frame buffer to as a render target for things like screenshots. So you want to be sure that you render to the one that we pass. And then going in line with this, of course, you'll want to be aware of asynchronous code. So patterns like this can be problematic because this code may execute outside of the custom layer. And then just briefly at the end here, I wanted to go into a little bit about what's next for custom rendering. So nothing's set in stone at the moment, but there are a few things we want to improve upon. So the first is that we want to simplify data integration. So the API offers a host of functionality for querying and handling a variety of different services. And we want to allow developers to leverage that functionality in their own custom layers. Additionally, we want to provide more structured ways of customizing rendering. So we want to provide a drop-in point for custom fragment shader code, as well as before and after draw hooks that developers can use to do things like run their own UI code or maybe even implement their own custom post-processing passes. Additionally, we want to improve integration with the rest of the API. So things like labeling we think is a major opportunity here, and we think it would be great if developers could create their own labels and have those interact with the other labels that are on the screen. And then lastly, we want to make it a little more accessible. So we want to provide ways for non-WebGL developers to further customize rendering, because we know that creating a WebGL custom layer can be quite a lot of work. And then, of course, we want to hear your feedback. Let us know what you want to see next, and that'll help us shape what we prioritize. And I don't think we have any time for questions, but we'll be at the island.
We're taking questions at the JavaScript island, so we're going to hand over there. So anybody has questions, you're more than welcome to follow us there.